equation, the two Maxwell's equations. We talked about complex intrinsic impedance, the complex propagation factor, how waves behave in highly lossy medium metals, and then low loss medium. No question if it's about the homework at all? Okay. I usually like doing one or two problems, but.
Can you work the first one?
Okay. Give me. You gotta tell me what it is.
It says, you talking about the one that's.
Yeah.
It says region 1 with z less than 0 has constitutive properties sigma equal to 72. No, I'm sorry, epsilon equal to 72. I'm sorry.
Epsilon?
Yes, sir.
Epsilon relative.
No, it just says.
It says epsilon.
Well, it's gotta be epsilon relative, 72.
Okay, that was the confusing
That makes
part.
sense.
Yeah, it would be epsilon relative. Go ahead.
Sigma equal to 5,000. Mu r equal to 1.
That's the relative permeability.
And electric field equal to 5e to the negative alpha z.
5 times e to the minus,
Alpha z
alpha z,
cosine 2 pi times 10 to the 9th t minus beta z. And it says,
in what ax direction? Or?
Yeah, but then it also has something else.
it also had a watt too.
It had AX and then it said like what units it was.
Yeah, it said units and then AY.
All right, thank you.
Right there.
Right here?
Yes, sir.
That's an accident. That's AY shouldn't be there. That's my bad. Honestly, I don't know sometimes how that happens, because I'm taking old homework and literally just putting it there sometimes. And I may modify one or two things, but that's my bad. I'll look at it more carefully. Anyway, for this problem right here, what are the questions they want?
Intrinsic impedance.
All right, now these are just gimmies in terms of what's, when you talk about intrinsic impedance, it's really going to be the square root of j omega mu over sigma plus j omega epsilon. That's the whole thing, right? For this one, there has to be a frequency, but how do we obtain the frequency? Just by looking at this. Anyone?
Divide omega by 2 pi.
Well, yeah, you said it, you're ahead of everybody. That's omega. So you identify omega, and that means if I divide by 2 pi, you see the frequency is 10 to the 9th hertz. Everybody agree with that? After we got that, we know omega is 2 pi times 10 to the 9th. Now, we can go ahead and just put it in here. We know that's just mu naught. This is 72 based on, or I'm sorry, this is 5,000 and this is 72. Let me write down exactly what this is. So we got nothing. This is the square root of j times omega 2 pi times 10 to the 9th times mu naught, which is 4 pi times 10 to the minus 7th. If you're smart, you put these in your memory of your calculators because you use them all the time. Some way to designate mu naught, some way to designate epsilon naught. Then it's over sigma, which is 5,000, right? Plus j, and it's omega, which is 2 pi times 10 to the 9th. Then it's epsilon relative, which is 72. Then epsilon naught. Epsilon naught, you can do it doesn't matter which way you do it, but I'm going to go ahead and put 8.854 times 10 to the minus 12th. That's farads per meter. Now you have the intrinsic impedance, right? They'll also want the propagation constant. Propagation constant is similar. It's the square root of j omega mu naught times sigma plus j omega epsilon relative epsilon naught. And these are straightforward, plug and chug. Yeah.
So for the intrinsic impedance, I was getting the right phase angle, but I wasn't getting the same magnitude as the solution.
Are you using this formula, people?
Yes, sir. I plugged it in straight.
When you do this in your calculator, what do you get for this?
I was getting like 1.26 at an angle of 45 degrees.
Anybody else?
That's what.
What?
What was the answer?
Like,
Like the solution.
It says 27.91.
Well, that's wrong.
Okay.
I mean, if you're telling me that calculation was done, then this is the way it's done. That's it. And if that answer's wrong, that's on me. I'll try to make sure it's right from now on. Give me the value again.
1.256 at an angle of 45 degrees.
All right, and that's ohms. And about this propagation constant, again, you're just plugging and chugging. What do you get for that?
That was like 4,000 something.
Well, why don't we give me the real and imaginary part? And the reason is the real part's alpha, the imaginary part's beta. So
Yeah.
give it to me in real and imaginary. Make sure you can do these on your calculator. Today I had the EMAG 1 class I'm teaching at 8. They had the classic equation they had to calculate for Zn is equal to Z naught times ZL plus J Z naught tangent of beta L over ZL plus J tangent of Z or J ZL tangent of beta L, and they messed it up. I mean, it was a quiz, and I'm going to say maybe 50% got it right. They just don't know how to use a calculator. What'd you get for this?
I think it was like 4.4 e to the third.
Well, hold it. 4.4 what?
Times 10 to the third
Times 10 to the third. Go ahead.
plus 4.4 times 10 to the third J.
Is that what you guys got? How many got that? I mean, did you get it, guys? Did you get it, Judge?
I hadn't worked on my calculator, I was writing something else down.
All right. If there's one thing to note, this is a good conductor if these two are the same. All right? If the real and imaginary part are the same, it's a good conductor. As a matter of fact, this is alpha. And this is beta. What else did they ask in our problem?
They asked for the phase velocity and wavelength.
All right. Phase velocity is 1.
Omega over beta.
Yep. Phase velocity is just omega over beta. Well, we've got omega, it's 2 pi times 10 to the 9th, right?
Yeah.
And beta is 4.4 times 10 to the 3rd, so what do you get for the phase velocity?
I got 1.4 times 10 to the 6.
That's what I got to do.
Now that's meters per second. That's fast, but it's a lot slower than 3 times 10 to the 8th meters per second. So it's 2 orders of magnitude at least below the speed of light. And if that was a good dielectric, then it would be approximately the speed of light if epsilon relative is about 1. What else did they ask for? Wavelength?
Wavelength.
All right, how do you get wavelength? I recommend this part, this way to get it. People do everything. Now think about what wavelength means. It means the argument here, forget omega t, but if I have cosine of beta z, you're going to have beta z equal to 2 pi. You go through a full cycle, right? It's from 0 to 2 pi. So beta times the wavelength is 2 pi, therefore the wavelength is 2 pi over beta. And this will work every time. And we have beta, that's 2 pi over 4.4 times 10 to the 3rd, right? And what do you see that's going to be equal to 1.4 times 10 to the 3rd, is that right? Meters or not? I'm sorry, minus. Sorry, what does this come out to? It's 1.4 times 10 to the minus 3rd, isn't it?
Yeah.
That's meters. Correct, class?
Yes.
What else do we have?
And then they want H in the phasor domain.
All right. If this is E here, I'm going to tell you, this is, does everybody agree with me it's a good conductor?
Yes.
And what would be the test to find out if it was a good conductor if we didn't know? This would be the test. Sigma is much greater than omega epsilon. So if you look at sigma 5,000, what's omega epsilon? Well, it's 2 pi times 10 to the 9th times 72 times 8.854 times 10 to the minus 11th, right? Or 8.854, sorry, times 10 to the minus 12th. Well, that is a much, much smaller if you calculate it. As a matter of fact, what is this value here? This we know is 5,000. It's stated explicitly. What's this value, omega epsilon? 2 pi times 10 to the 9th times 72 times epsilon naught. And you can use 1 over 36 pi times 10 to the minus 9th if you want. It's like 4. This is 4. All right, now y'all can see that 5,000 is much greater than 4. This is a good conductor, correct? Now, if we're in a good conductor, we know that the E field and the H field will be out of phase by 45 degrees. I don't know if you realize that or not, but I'll show you. Normally to get H, first let me do it this way. Let me put E in terms of a phase. if E wanted to be reckoned as a phasor, it would be E naught or 5, right? Then it would be e to the minus, I know it's got that alpha, I'm just gonna leave it as alpha z times e to the minus j beta z, right? And then it's in the ax direction. Now to get h, the way you get it in the phasor is 1 over the intrinsic impedance. That's the intrinsic impedance, so it's 1.256. The angle is 45 degrees here. When it comes upstairs, it's going to be e to the minus j 45 degrees, or pi over 4 radians. So this is really, I'm just taking 1 over the intrinsic impedance, but the intrinsic impedance, I'm taking the angle upstairs. Y'all follow me on this? Now the next thing is the unit vector in the direction of propagation, that would be az, because when we look here, we see beta z has a negative sign in front of it, right? That means it's propagating the positive z direction, got it? It's az crossed into the E field. Well, the E field is here. That's 5 e to the minus alpha z e to the minus j beta z ax. And you can see here for h, when I do that, what do I end up getting? I'm going to have 5 over 1.256. Then I'm going to have my e to the minus alpha z. The alpha is this value. I'm going to have e to the minus j beta z. But I'm also going to have something else. I have 45 degrees here as a minus sign, so it's plus 45 degrees. Do y'all see that, class? Now that's in the phasor domain. If I wanted it in the time domain, what would I do? It would look exactly like this except for one thing.
Phase
It would be beta z what?
plus.
No, minus 45, right? Because it's minus 45, right? And then there would be, and instead of being in the x, it would be the y direction. So if you wanted it in the time domain, then it would be this value, 5 over 1.256 e to the minus alpha z. And then it's going to be cosine of omega t minus beta z minus 45 degrees, right? And that's a y. So that would be a y. What else do they want? Okay. If I wanted power, how would I do power? The Poynting vector, the power density flow. This is a good conductor. What would it be? Technically, it's 1/2 the real part of what? E cross H conjugate, right?
Yeah.
Well, I'll tell you from practice, you do enough of these, it sticks with you. I know what's going to happen here. I'm going to have 1/2. I'm going to have the magnitude of the E field. Then I'm going to have the magnitude of eta here. That's the magnitude. Then I'm going to have the cosine of the angle associated with the intrinsic impedance. In this case, it's 45 degrees. Y'all with me on this?
Yeah.
It's going to be that. Then it's going to be multiplied by e to the minus 2 alpha z, and it's in the, and there is no, for power, you don't have a direction. It's flowing in the z direction, but this would be it. It's actually, there is a direction to it. It's a z, because you take e cross h conjugate. E is in the x, h is in the y, therefore the what's left over is in the z direction. Do you all follow me on this?
Yeah.
Now this is a single number, and that would be the power at z equals 0, if you call it p0. All right? Any other questions?
We do 6.26.
Now you're gonna have to give me the specs.
Okay, it gives HCFT.
Pardon?
It gives you the H field, and you determine the power passing through a 1 square meter surface that is normal to the direction of propagation.
All right, well, let me erase this. I'm trying to. All right, now say it again.
H is equal to 12 cosine pi times 10 to the 6 t minus beta z plus pi over 6.
Plus?
Yeah,
Pi
plus
over
pi over
6.
6 in the AX direction.
Okay.
Amps per meter.
That's per meter.
wanna determine the power passing through a 1 square meter surface that is normal to the direction of propagation.
Alright, first we gotta find the direction of propagation. By looking at this, what is it?
Z.
Yeah, you look at the coefficient of beta. It's z, right? And it's a negative sign, so it's going plus az direction. So a rho is equal to AP is az. That's a unit vector in the direction of propagation. Next, I'm going to put this in terms of a phasor, all right? The phasor form of this would be what? H, technically vector phasor, it would be equal to 12, right?
Yeah.
And it would be E, you'll notice there's no attenuation. It's just e to the minus j beta z, right? And there's going to be also, I'm going to break that phase out by itself. And it would be e to the, and this is going to be plus j pi over 6. Do you all see that, class? There's a pi over 6 that's in there. This is going to be in the AX direction. That's the H field, right? How do you get the power? Well, technically power average is a function of z. I like using script x because that's the pointing vector that you'll see over and over again in journal papers and stuff. That's very common. SAV is going to be equal to 1/2 the real part of E cross H conjugated. Here I'll make a statement. I can say that from H I can get E, and E is simply equal to minus eta times A rho crossed in to the H field. Do you remember that one? That's where the negative sign comes in and eta is on top. Now when you take a look at this, does it say anything more about this problem? They don't give anything else?
Other than just it's passing through a 1 square meter surface that is normal to the propagation.
All right, well, they don't give you a value for beta? All right, now, when you...
Oh, wait, it's in there.
What is it?
It says it's in air,
All right,
but.
that's, if it's in air, that means the phase velocity is equal to c,
Yeah.
and because of that, what we can do is say the intrinsic impedance is just 120 pi, because it's in there. So this would be equal to, I'm just gonna leave it as eta naught, and it's gonna be minus eta naught AZ crossed into the H field. Well, that's the H field, so it's crossed into 12 e to the minus j beta z, right, times e to the j pi over 6 in the AX direction. So if I cross that, I get minus eta naught times 12 and times e to the, I'll put a j pi over 6 first, times e to the minus j beta z. And I have z crossed into x is what, class? AY, right? And that's going to be the E field. Then to get the power, I'm not trying to block you here, sorry. So that's just doing a definition, right? And then to get the power here, that's 1/2 the real part. And I know because it's in air, there will be cosine of the angle is 0. You follow me? I know it's cosine of 0, I'm sorry, it's 1. Cosine of 0 is 1. So this is going to be 1/2 E, which is this. So it's one real part of eta naught times 12 times e to the j pi over 6 times e to the minus j pi over pi z, beta z, pardon me, ay. And that's crossed into the H field, which is 12 times e to the minus j beta z, but it's conjugated, so it becomes plus j beta z. And then times e to the minus j pi over 6. This is because of conjugation. And it's in the AX direction. Right? And that means it's 1/2 times eta naught times 12 squared. And everything cancels there. And that should be it. I'm gonna show you a trick in a second. You all see what I've done? What do you get for that? You got 12, really, do 12 over 2 is 6, right? And then you got 6 times 12, 72 times 8 or not. Give me a number.
It came out to 27 kilowatts.
27 or 27 kW per meter squared. Now, how big is an area is this power flowing through?
1 square meter.
I guess it's 27. Is that the answer? Okay. All right. Because otherwise, you'd have to multiply the power density by the area it's penetrating to find out the total amount of power. Power density is watts per meter squared, right? To find out watts, you have to multiply it by an area. Anything else? All right. Hmm?
I was just making sure I had it all down. I understood it.
These are pretty straightforward, but I'm going to show you a trick to these. If you're in air or free space, if you're in air, this is where epsilon naught, mu naught are the only things you're worried about. Then the power density, S av, equal to P av, this is a vector quantity, is always going to be 1/2 the magnitude, mind you, of the E field divided by eta naught. And that's the same thing as 1/2 eta naught times the magnitude of the H field. Those are identical. If you think about back in the day when you had power through a resistor, it was what? 1/2 magnitude of I squared times R, right? Or 1/2 times V squared over R, right? So voltage is like electric field. You divide it by the impedance, right? Current, or H field is related to current density, really current. So you multiply it by the impedance, and that's something to keep in mind. And there's no phasing. I mean, you don't have to worry about a cosine anything that's in here.
So this is only for air.
Well, yeah, and if it's lossless, you don't either. But if it's
Yeah.
lossless, then eta changes. The value of eta is not 120 pi. Okay. Anything else? Excellent. All right, now today we're going to do a topic. This is I didn't mention standing wave ratio, but I'm just going to bring it up briefly. You remember back when you had transmission lines, the standing wave ratio was the ratio of the largest possible voltage to the smallest possible voltage on the line, right? In magnitude. Well, when we talk about the standing wave ratio, is there any place around here is there any wastebasket that you guys see back there? Right there?
There's one that's like right outside the room.
Would you go and bring it down here for me, please? And this is going to go into it, courtesy of me. All these bad markers we're going to eliminate. All right, now, anyway, the standing wave ratio is standing wave ratio is just the magnitude of E max. It's really E maximum value over E minimum value. Now, if you think about this, none?
Big trash cans?
No, it should be a little, nothing small back there?
Not a little one back there.
All right, we'll just throw these things out at the end of the class. Well, when you think about the E field in general, what do you think about? The E field is of the form sum E naught, right? And then it's times e to the minus j beta z. This is for a plane wave. Plus the reflection coefficient times e to the plus j beta z, right? Now, I'm going to explain something to you. Beta z is an angle. It represents an angle. Follow me? Now, this one's turning in the counterclockwise direction. This one's turning in the clockwise direction. Does that make sense to everybody? Or vice versa, it depends on your perspective. So let me show you something. If I have this being the real part, and this being the imaginary part, or J, when I talk about something that's got a magnitude of E naught here, and it's at a phase angle of beta z, that should make sense. This would actually be a positive phase angle. This would be E naught, e to the plus j beta z. Are you with me? Now watch this. So I've got something out here, I don't know what beta z is, but that's E naught. Then I got this vector here. Actually, you know what I need to do? I need to multiply that by gamma. So it's gonna be magnitude of gamma times magnitude of E naught, and then it's gonna be times E to the J and beta z plus the phase angle associated with reflection coefficient. And that's really what this vector is. If you think about this, suppose this is E to the J 60 degrees, and this is like 2 and an angle of 30 degrees, right? So it'd be 2, right, would be the magnitude, and you would have to add the angles. Do you follow me on this? So anyway, this is where this is. It's got some magnitude here, and it's at this angle. That's the total angle. Now, and it's rotating this way. Now there's another vector here. It's e to the minus j beta z. And it has a weight of E naught, only E naught in front of it. This has got E naught times gamma. Now you all see that this angle here is beta z. Can you all see it? Everybody? Now just look at this and rationalize it. What's the maximum possible this can be when you add these two together? If I added them right there, it would be tip to tail, and this would be the result. Do you all see that? But you should be able to see in your mind's eye that if these two were in the same direction, you would have the greatest possible value. Does that make sense to everybody? When they came together, like if they're rotating, when they came together, when we're right here or right here, wherever it would be, then both aligned on the top, like two clock hand, like the minute hand and the hour hand on top, right? If you're gonna add them together, it's tip to tail. You all see this? And the real value would be, the maximum value would just be E naught times 1 plus the magnitude of gamma. That would be the maximum value. Does that make sense? Now what's the minimum value? Just think of these hands of the clock as they're winding. Well, the minimum value would be when they're pointing opposite each other, right? Then you're doing tip to tail addition, so you would be subtracting one from the other. Then you would get this. It would be E naught times magnitude of 1 minus the magnitude of gamma. Now it's important you put magnitude of gamma there. It's really, frankly, the best way to do SWR is just say it's 1 plus the magnitude of gamma over 1 minus the magnitude of gamma. And that's at the load, by the way. That's, or I should say, not just the load, it's the reflection coefficient at the barrier between two media. With me? You have standing waves or reflective waves, you have to hit something to get a reflection. So it's the reflection coefficient at that barrier. I want to ask you one thing. Look at this value for SWR. What's the minimum value it can have? Well, the ratio of min to max would be what? Now, this is not in the time domain, this is in the phasor domain. So if you think about a transmission line that goes on forever, or you talk about free space that goes on forever, and you launch an electromagnetic wave, well, there's no reflections, right? That means really the value of the E field, the magnitude of the E field is the same everywhere. So the standing wave ratio, well, the minimum value and the maximum value of the same would be 1. And that's when the reflection coefficient is 0. So the maximum value, minimum value is 1. But what's the maximum value? Look at that. Look at gamma. Gamma is a reflection coefficient, right? It can go to 1 too, right? Or minus 1, right? So what happens? Well, when gamma is plus or minus 1, then the standing wave ratio goes to infinity. You all see that? So just remember that. Standing wave ratio gives me an idea of the relative amount of peaks and valleys, the size of them. Standing wave ratio is used to, standing wave ratio of infinity means in the area where the wave is propagating, there's points in space that have absolutely no electric field, and there's points that have twice the actual incident electric field magnitude. That's one of these things that, think back to transmission lines with SWR. You remember that? All right, so that's important. Now, the next thing I'm going to talk about, and this is a little more complicated. It happens to be a Friday, which is not a good day to do business with complicated things. But this is going to be very important. This is going to be oblique incident. Now we're not hitting things normal, we're coming at an angle. I'm gonna draw this up here. There's two forms of it. One is called perpendicular polarization, the first one we're gonna talk about, and the other is parallel, and I'm gonna explain this. When I teach radar, we don't do that. We call that one horizontal and the other vertical polarization, because everything is with respect to the ground. And I'll show you what I'm talking about. Suppose I have a media. This is going to be media 1 and media 2. And then draw a straight line through there. Call this the z direction. Let's let that be the x direction. Now, I'm going to do this in the simplest possible way. This is called transverse electric field, or perpendicular polarization. Now, what is perpendicular polarization? It's this simple. You see that this is x and y, that the plane wave is traveling in this plane. It's going to hit, I'm going to be honest with you, I'm just going to say it's going to come in at this angle. That's going to be the incident angle. And it's going to reflect back at this angle. I can tell you right now that the incident angle is the reflected angle. And some of it's going to be transmitted at a different angle. Right? But what perpendicular polarization means, or transverse TE polarization, the typical thing it's TE is this. The electric field is perpendicular to the plane it's propagating in. Follow me? Now it also means this. When the electric field hits the surface, it's exactly parallel to it. Do y'all see that? That surface comes in and out of the board. Do y'all see that? So the electric field is perpendicular to the plane it's propagating in. It takes a while to appreciate this, but an electric field, I'm just using this magic marker to identify the actual polarization direction, right? It's propagating like this. So the electric field here is going to be out of the board. The way you signify out is you put a little circle and a dot in it. Now, I know that E crossed H is the direction of propagation. Do y'all remember that? E crossed H is power, and the direction of power flow is the direction the wave's moving. Well, if E is out of the board, I know H has to be perpendicular to it, and my thumb has to be in that direction. So I know the H field will look like this. And that's the incident H field. I'm going to describe these mathematically in a second, but I want you to appreciate the way they look, or the appearance. Can you all understand that? Now, this wave comes in, there's an E field coming out. It hits here, and it's reflected. That means we're going to have a reflected wave here, right? That's incident, H. Now that's H, this is E, incident. This is going to be E reflected. And which way is the H field going to be? Take a look at this. It's going this way, right? It's reflected. So E crossed into H has got to be in that direction, right? That means the H field looks like this. And that's H reflected. I'm doing my best. Can you all appreciate this? Guys? E crossed H is the direction of propagation. If I've got E, I know the direction of propagation, I can figure out what H is. All these three vectors are always perpendicular to one another. Now, there's also a transmitted field. The E field will always be out of the board in all these cases. It doesn't reflect back in some other way. It's always got the same orientation. And the H field for this one is going to be in this direction as well, just like the incident. This is the transmit. And it's going that way. Now, there's a good drawing in the booklet on this one. You can tell me the page if you have it.
361.
What is it?
361.
Yeah, it's good to have your book here. So what I'm doing is just re-expressing what's in his book already. Now watch this. So now I need a mathematical description of this. Here's where it gets a little hairy, so I want you to understand, I want you to pay attention. Suppose I have this coordinate system. I have Z and I have X. But I want a different coordinate system. I want to cast points from this coordinate system into a different one. Please listen. So suppose my new coordinate system is this. I'm going to have something called the Z prime axis right there. Do you follow me? As a matter of fact, let me do it this way. I've got something, and this is the Z prime axis, it's this way. So when I take a look at that, if I wanted to know what Z prime is in terms of Z, let's use this value of Z, and let's use this value of X, whatever they are, call it X1 and Z1. Then Z prime would be equal to, now you're gonna have to watch me on this because this gets crazy. This is gonna be the same angle as this, and we're gonna call that the angle of incidence. Because what I'm trying to do is replicate this. This is the angle of incidence. Remember that if I drew a straight line through here, it would be opposite interior angles are the same in geometry back in the day when you were in high school. So when I look at this, my Z prime, now please watch. If this is Z, right? And this is the hypotenuse of a triangle. The edge that's nearest to a right triangle, and by the way, this is a right triangle right here, would be equal to, it would be Z, right, times the cosine of the incident angle. Now think about this. If this is Z and I want the projection of this on Z prime, since that's 90 degrees, I would take the cosine of this angle, right, and I'd multiply it by this. Do y'all see that? But I'm not done yet. Now for X prime here, if I keep going, since it's there, this part, and I didn't draw this very well, should be up here. This part right here, this would be the same angle as this. And what I would have is the value of X right here times the sine of the angle. And that would transfer both X and Y into a value in the Z direction, right? It's sort of like doing the cartoon. Remember when you had X, Y, and Z and you turn it into cylindrical coordinates? The radial distance was always the square root of X squared plus Y squared, right? Same kind of deal here, only now it's a projection onto this thing. And by the way, what I should do is this. It should be this. It should look like this, being there. Right there. And that's not drawn too well. But this, he has this in the book, doesn't he, guys? I know he does. He shows Z prime equal to that, right? Well, he will, and let me just show you why. Because you see this thing's propagating in this direction, the Z prime direction, right? Now listen to me. That means the E field here, the incident E field, can be expressed as E naught. Normally it's just E to the minus J beta Z, right? But now it's E to the minus J beta Z prime, with me? In the A Y direction. Remember, it's moving this way. It's coming in an angle. Understand, everyone? And furthermore, because it's coming in on that angle, we're going to write this in terms of Z prime. And I want to make sure you understand one thing. In this domain, there is beta 1 and there is eta 1. In this domain over here, there's beta 2 and there's eta 2. There's two different sets of values for propagation constant and for eta. Follow me on this, everyone? Usually this is eta, but not always. Okay, now please watch this. It is a little hairy. If you have your books, you can follow along in the book. You don't need to write this down. It's specified really well in the book. And again, this is TE polarization. So now we need to describe this. How do I describe this incident field? Well, I always start at some E naught incident. That's a scalar value, 5 volts per meter. Then I multiply it by the phase change, which is E to the minus J. It would be beta 1. And then instead of putting Z prime, now I put in X times the sine of theta incident plus Z times the cosine of theta incident. And this is going to be in the AY direction. Are you with me, everyone? That's the E field. I want to get the H field in that direction also, right? To get the H field, normally what do? And if you've got phasors, this is a phasor, right? Vector phasor. H field vector phasor of incident would be what? 1 over eta 1, A rho, unit vector in the direction of propagation, crossed into E incident, right? You agree with me? All right, what's the unit vector in the direction of propagation? This is one you got to pay attention to. It's not propagating the z direction, it's not propagating the x, it's propagating in this direction, right? Can you all see that the unit, if that's a unit vector of 1, I'll do it this way. If this is a length of 1, right? And we take a look at the projection, I'm trying to do this without complicating. On this axis, the z-axis, that would be 1 times the cosine of theta incident, AZ, and on the vertical axis, it would be 1 times the sine of theta incidence times AX. You see, if you have 1 at that AZ, and this is the angle we're talking about right here, you see the cosine would be the multiplier to project it onto the z-axis, and the sine would be the multiplier to project it onto the vertical axis, the x-axis, right? So now I can say that with that in mind, my unit vector in the direction of propagation is simply equal to cosine of theta incident times AZ plus sine of theta AX. Does he have that in his book? I'm sure he does. You're looking? All right.
Negative cosine AX.
Yeah, he has it.
No. Vector direction. This is it's a unit vector in the direction of propagation. Isn't it going positive for both for the incident angle? You're looking at the answer for H, aren't you? This is a unit vector in the direction of propagation. It's propagating this way, right? So it's got to have a plus z, a plus ax, right? So that's it. That's a unit vector in the direction of propagation right here. Now I do this. I say that H incident is going to be 1 over a to 1. This, which is going to be, I'll put the sign first. Sine theta I ax plus cosine theta I a z, and I have to cross that into the E field. This is the E field. So it's E naught incident, and it's e to the minus j beta 1 x sine theta plus z cosine theta incident, right? And that's in the AY direction. This is a little messy. It's bookkeeping, but you got to do it. Remember, these are plane words, right? Are you with me? Now keep going on this one. Y'all see that this stuff right here, this E naught, this E to the stuff, and this 1 over eta, that can come out in front. I can say that H incident is really going to be equal to E naught incident over eta 1 times that E to the minus j beta x sine theta plus z cosine theta incident. Those are theta incident. That's messy. And then what I can do is this. Now I can take sine theta incident. AX crossed AY is what, guys?
Z.
AZ, right? So I can take sine, I'll put it out here, sine of theta incident, AZ, and along those lines, what happens when I have Z cross Y?
Negative X.
Right, then I get minus cosine, right? Theta incident, AX. And that's my H field incident. Y'all follow me on this? It's a little weird because you got that X sine of theta incident plus Z cosine theta incident to represent Z prime. And the unit vector is different than you're used to, right? You'll work through it, believe me. So that's my H field incident. And that's my E field incident. There's E, there's H. Now I'm going to tell you this. For the transmitted field, it will have the same exact form. We could work through it, but the only thing different is the angle cosine, the theta, it's not theta I now, it's going to be theta transmitted, right? It's the angle transmitted. That's this angle. So I'm going to put that up here. I can say that E transmitted is going to be some scalar value, E naught transmitted, and it's going to be times E to the minus J, now it's beta 2 times X, but it's going to be sine of the theta transmitted plus Z times cosine of theta transmitted, and it's in the AY direction. That's E transmitted. H transmitted will be the same as this, The reason I know that is because y'all see that the relative direction for the E field's propagation is upward. It's in the positive x, positive y. You all see, or positive z. And the orientation is out of the board. Well, here it's the same thing. E field's out of the board, it's propagating upward, right? Positive z, positive x. I know it'll have the same form with angular differences and values of beta and eta slightly different. So this is going to be E naught transmitted over eta 2, right? It's going to be e to the minus j beta 2 times x sine theta incident plus z times cosine theta incident. But here, now we're going to have sine of theta incident like he has here. Well, actually I should put the cosine first, I guess, because we want to say x. Minus cosine theta incident ax plus sine theta incident az. Are you with me? I see books open. Do you see this in his book? This is for TE polarization. It's the very first part. And he'll have transmitted and he'll have incident, right? Now the reflected field is a little different. And I want to do the reflected field. I want to leave those two up. I'm going to do it right here. Now when we talk about reflected field, it's going to be some E naught reflected. But here's the difference. Which way is this traveling? Take a look at the unit vector in the direction of propagation. This angle is the same as this angle, right? It's going in the positive x but negative z. Do you all see that? So that means the unit vector in the direction of propagation for the reflected wave would be equal to, here, it's going to be, it's still going to be the sine of theta ax, but it's going to be minus cosine of theta reflected az. That's because it's going in that direction. You all see that? And now I do it this way. I just put down e to the minus j beta 1, but now I put down x sine theta incident, but it's going to be minus z times cosine theta incident because it's going in the negative direction, in the negative z direction. And it's going to still have an AY orientation. Could you take a look in the book and see where this is? This is for the reflected field. Take a look at that. It will have an E naught reflected. Do you all see that in your book? All right. It's going to have e to the minus j beta 1, right? Then it's x sine theta reflected, actually reflected, but reflected and incident would be the same. And then it's going to be minus z cosine theta reflected. You all see that?
Yes, sir.
That's the important part. Now to get the H field for this, H field reflected, it's going to be again 1 over eta 1. Unit vector in the direction of propagation has got that negative sign here. You don't have to do this all the time. So I have sine of theta reflected ax minus cosine of theta reflected az, right? And then I have that crossed into the E field right here. You don't have to write it down. You've got it in front of you in your book, but you got to appreciate what's going on here. I'm not going to ask you to reproduce all of this at any one point, but I may ask you to derive something based on an understanding. If I give you, say, E transmitted, and I ask for H transmitted, and I give you a drawing, then you should be able to come up with it based on your knowledge of basically this. Got me on that one? But I don't ask difficult things just to irritate you. I'm trying to make sure you have an appreciation for this. It's important. And again, this is the way we describe them mathematically for plane waves. It's simply a description that's useful for everything else we do, like calculating power, reflection coefficients, and all that. All right, now I have that. Let's go through this. What is that going to be? H reflected, y'all see that this crap right here, I mean all that, and eta 1 can come out in front. So it's equal to E naught reflected over eta 1 e to the minus j beta 2, not eta 1, yell at me, eta 2. Oh, I'm sorry, eta 1, eta 1, this is beta 1, times x sine of theta incident minus z cosine of theta incident, right? That's just the scalar stuff, all that. Then, when I have x crossed into y, I get x crossed y, so you have the x crossed into y is z. Right? So now I'm left with sine of theta reflected az. And when I have z crossed into y, it's z.
Negative X.
But there's a negative sign, so it's actually positive. So it's going to be cosine theta reflected AX. And that's the descriptors for the transmitted and reflected electric field and the incident electric field in a phasor domain coming in an oblique incidence. Now I know this is difficult to really grasp the importance of it and remember everything. But just remember the way you get it. You write a description for the E field, you get the H field from saying 1 over eta, unit vector in the direction of propagation, crossed into the E field. Got me on that one? So now, why did I do that? Because at this boundary, we're going to get the transmission coefficient and the reflection coefficient for TE, okay? This is why I wanted to do this. And I know this is a little, it's tough to slug through here if it's a nice day, you're tired, it's Friday, but we're gonna. I have to go through the theory for you to appreciate everything else I'm gonna do. So leave this stuff up here, that's incident, right? Now, at the boundary at z equals 0, I want you to watch what happens. At z equals 0, that's the boundary between the two regions, right? There's two things that happen. You have E tan 1 must be equal to E tan 2. This is at z equals 0, it's the boundary. So you have E tan 1, the tangent electric field in region 1 has to be the tangent electric field in region 2. And H tan 1 has to be equal to H tan 2. When I say tangent, it's the value of the electric field that's parallel to that boundary. You follow me on that, class? And the value of the magnetic field that's parallel. So remember the way it looked. That was equal to z, that's x, this is region 1, this is region 2. So we know the x components of both E and H are tangent. Do you all agree with that? People? It's not the z components. Actually, I'll go a step further. It's both x and y, because y is coming right out of the board. So x and y are parallel to that boundary, because that boundary comes straight out of here, right? It's in a sense, we're taking a look at just a cross edge, but this is supposedly comes all the way out here. All right, so now, when I do this, I'm going to take E tan 1 as E tan 2. This is important. In region 1, we have two electric fields that we have to worry about, the incident and the reflected. You follow me? When I look at the incident and reflected field, well, this is the incident, it's in the y direction. This is the reflected, it's in the y direction. If z is equal to 0, right, I can get rid of that and get rid of that. So for this region 1, I'm going to have E naught incident times e to the minus j beta 1 x sine theta incident plus E naught, this is incident, plus E naught reflected times e to the minus j beta 1 sine, this sine theta incident x. That's the tangent value in the y, it's oriented in the y direction on in region 1. It's got to be equal to the tangent value over here, which is the transmitted field. E naught transmitted times e to the minus j beta 2 times sine theta 2 times x. This is a real important point. Does everybody see how I get this? I said z equal to 0, and I equate the tangent values of the E field at that surface, right? This is a very important point. Now, if this is true always, I want you to listen. this is true always, then this phase angle, e to the beta 1 sine theta incident x has to be equal to beta 2 sine theta 2x for all values. The only way it can be equal to, for all values of x is if beta 1 sine theta incident is equal to beta 2 sine theta incidence. What I'm saying is, if you look at this, just think about it. If I have e to the minus j, say 10x, is equal to e to the minus j ax. The only way that can be is if a equals 10. Does that make sense to everybody? For all values of x. It's true if x is 0, you can have any value for a. But for all values of of x, there's only one thing that can happen. That the angular values have to be equal. And what that means is this. This angle has to equal this this value has to equal this value has to equal this value. So I'm going to do it. Beta 1 times sine beta incident times x is equal to beta 1 times sine, or this is, yes, sine theta reflected, that should be reflected, x equal to beta 2 sine theta 2, or transmitted, really, theta transmitted times x. What do you see happening here? The only way for this to be true, for this one, is for theta incident to be equal to theta reflected. And that means the angle of incidence is equal to the angle of reflection. How many of you here have played billiards or pool? All right, if you play billiards or pool, what do you notice? Usually, unless you put a lot of English on it, the angle into the surface of the billiard, or the rail, is going to be the angle it bounces off. It's the same way with electromagnetic energy when you're talking about planar surfaces. Understand that, class? Same deal. So angle of incidence is equal to angle of reflection. The next thing that happens is this. This has to be equal to this. Has to be equal to this. So then we get something called Snell's law. Snell's law is very important, and that says beta 1 times the sine of theta incident is equal to beta 2 times the sine of theta transmitted. That's Snell's law. You all heard of Snell's law before in physics, right? That tells you how something bends, how the actual direction of the electric field rays, or flashlight you flash, how it bends in different media. Well, what do you know about water? Like if this is a water surface right here, this is a surface of water and that's below it. If a wave's coming in and it hits, because water's dense, it bends just almost going straight down, doesn't it, class? Well, that's because of this law. Because water has a relative dielectric constant of about 81, somewhere in there. Depends on how salty it is, but so that means, well, we could do that problem later, but y'all follow me on this? So that'll tell you how much it's going to bend. This is Snell's law. It's very, very important. So we got that. And now there's another thing we're going to get. I'm going to tell you this right now. I've got 15 minutes and I know you got a quiz going. When I go ahead, I can go ahead and get the reflection coefficient. The reflection coefficient is given this symbol. This is the reflection coefficient. And that's equal to E reflected over E incident. Now in his book, please look at this. The way you derive it is this. You said Z equal to 0. And then what I do, since I've got the E fields here, this equated the E fields, right? The next thing you do is take the H fields. Now, what do you notice about what part of this H field is going to be parallel to that boundary? Just look at it. Here's an H field, right? Right here, right? The boundary is what? X, Y, right? This component is going to be parallel. Not this component. AZ is perpendicular to the surface, isn't it, class? So it's that component of the incident field. What about the transmitted field? This component, right? And what about the reflected field? This component as well. Do you follow me on this one? So when I say, I know it's getting a little late, and I'm running out of time. When I want this, what I'm going to do is equate these things. I may do it next time because I'm just about out of time when you get in the quiz. I want to tell you one thing though, please listen to me. The reflection coefficient and the transmission coefficient for the TE1 is in your book, all right? On what page? All right, that's for TE. There's a different polarization. That's when the electric field is not perpendicular to the plane it's traveling in, but in the plane, and that's called parallel polarization. I like to call it transverse magnetic polarization, TM polarization, because the magnetic field is then perpendicular, not the H field, or not the E field. I'll give you a quiz in 1 second. Would you do me a favor and separate yourself by at least one seat or more? Move all around the room. And for this quiz, it's closed book, closed notes, but you are allowed a calculator